Hello, Renaissance Woman here, and welcome to the second part of my 10-part seminar series on multivariate statistical analysis. For this video, we will be looking at a mean comparison method for multiple means called MANOVA, and there is going to be an R demonstration segment for this seminar. For this video, we will first look at the definition of MANOVA, the assumptions that must be met in order to perform it. We learn about two types of MANOVAs. The first one is called the one-way MANOVA, which involves only one group variable. And the second one is called Factorial MANOVA, where we are dealing with more than one group variable. Then we go to the R demonstration segment, and we are going to perform MANOVAs on a one-way example and a factorial example. And then we will end the video by looking at something called a partial Eta-Squared value. The partial Eta-Squared value basically it's something that we calculate in order to understand how much variance of the outcome is explained by the group variable for the one-way MANOVA, or group variables by the factorial MANOVA. So first of all, we go to the definition of MANOVA. MANOVA stands for Multivariate Analysis of Variance. And as you may be able to guess, MANOVA is the multivariate extension of the ANOVA, which is Analysis of Variance. Just like Hotelling T-Squared test is the multivariate extension of the t-test for means of two groups. Now, we can see here that for a t-test, we are trying to compare the scalar means of two groups here. But for the multivariate, when we have three variables as the outcome to be whose means we are trying to compare, compared to when we only have one outcome whose means we're trying to compare. The Hotelling T-Squared test, we have two groups that's being compared, and these are the means of the outcome variables. Okay? As for ANOVA, we are not comparing the means of two groups like the t-test here. We are trying to compare the means of more than two groups. So ANOVA can compare the means of infinite number of groups here. I only put 4 here, but this shows that there are infinite number of means to be compared, and this can be done with ANOVA. But for MANOVA, it's the multivariate extension of ANOVA. So instead of comparing infinite number of scalar means, we are comparing infinite numbers of mean vectors. So when we have a mean vector, we have three outcome variables whose means we are trying to compare with the three means from other groups. So there are infinite number of groups, and these are scalar values for only one outcome, and these are for three outcomes. So a good place to use MANOVA is, let's say we are trying to compare the mean scores of student grade, self-perceived happiness, and physical health from 30 students between 4 different North American countries: Canada, United States, Mexico, and Panama. And these are the means of these 3 variables from a data set. So we are trying to see if these mean vectors are significantly different between these 4 countries. That's when we use MANOVA to do. Now, these numbers, they are not actual numbers for these variables in these countries. So Canada, US, Mexico, Panama, please don't be offended by these numbers. I just made them up. Now, there are 3 assumptions about the data that must be met before MANOVA can be carried out. And the first assumption is the independent observations assumption. So MANOVA works best when the variables, the 3 or more outcome variables, the multiple outcome variables that are under comparison between different groups. If these variables, they can have only a moderate correlation amongst each other, but not too high, this works best for MANOVA. And in order to test this, we can use the intra-class correlation value. So these values, they can easily be calculated using R. And the ICC, it's a value between -1 and 1, with -1 means very strong negative correlation, with +1 being very strong positive correlation. And the second assumption and the third assumption, they are the assumptions that we also have to consider in the Hotelling T-squared test. For the normality, it's just the same thing. We test it using Shapiro-Wilks test, just like Hotelling T-squared test. So this is to make sure that the variables, the outcome variables that are under, whose means are under comparison between the groups, have multiple normal distribution. And the equal variance covariance matrices between groups assumption, of course, we have to have equal variance covariance matrices for the outcome variables between the groups that we are trying to compare them between. So this one we tested by box M test. I've already discussed how these ones work at the Hotelling T-squared presentation, which is the first seminar of this 10-part series. Now, there are 2 types of MANOVA. The first one is called the one-way MANOVA, when we are comparing a vector of means, when we are comparing the means of the outcome variables jointly through using one group variable, so that we can compare the mean vectors between the categories of this one group variable only. Now, let's say if we have more than one group variables, if the individuals of this data set can be classified in more than one way, we need to use a factorial MANOVA method. Before we get into the one-way MANOVA, we need to first understand the idea of ANOVA, which is for comparing the means of one outcome variable between several groups. In this example, we are looking at whether the grades of the students are different between 4 countries. For the analysis of variance method, the ANOVA, basically what we are doing is looking at how much the variance of the data set, which is the sum of square of the deviation of the data values from their means that are explained by the group variable And in this case, the group variable is the country variable. This compared to the variance in the data set that are not explained by the country variable, which is this error sum of squares right here. We do this by first calculating the sum of squares of the differences between the data caused by the group variable and not caused by the group variable. The one caused by the group variable is this sum of squares for groups right here. The one that's not caused by the group variable is this sum of squares for just the errors right here. We take the means of these sum of squares, and that's calculated by dividing it by their individual degree of freedoms right here. So now we have the mean square values that's explained by the countries and by the errors. We take them and we use them to calculate the F value. And then we can take this F value to the F distribution table so we can look at whether or not the variance that was explained by the country's variable, the group variable, is higher than the variance that's explained by just the errors. And we are going to get a p-value for this. If this p-value is below 0.05, then the country's variable is shown to significantly influence the student grades. And in this case, we can reject this null hypothesis that the means between the individual groups, they are the same. We can reject that. So at least one of these means are different due to the country of origin. Okay, so now that we've seen the ANOVA table again, this time we look at the MANOVA table. Now, the MANOVA table is different from the ANOVA table in the way how sum of squares are calculated. So for ANOVA, the sum of squares are calculated like this. So we have a total sum of squares. How we calculate all the variance, so all the differences from the means in the data set, and it's composed of the sum of the variance that are explained by the groups and the variance that are explained by the errors. So this is how you calculate the variance the sum of squares explained by the groups, and this is how you calculate the sum of squares that are explained by just the errors, not by the groups. And these values in this equation for ANOVA, these y's right here, they are all scalar values. So 1 is just 1, 2 is just 2, it's just one number. But for MANOVA, because the values that we're trying to consider, the y values, they are basically from more than one variable. So these values are vectors. Okay, so these values are vectors. So when we have a vector and we do this and we multiply these vectors by themselves, we get a matrix. So because this part is a matrix and this part is a matrix, we get a matrix for the total sum of squares as well. So when we look at the one-way MANOVA table here, the sum of squares are no longer called the sum of squares. It's called the sum of squares and cross products matrices. So for the sum of squares that explains all the group, that explains the different groups, we have a matrix here, and for explaining the errors we have a matrix, and for the total sum of squares we have a matrix here. So this H, it stands for the hypothesis sum of squares and cross products matrix. For this E, it stands for error sum of squares and cross products matrix. And for this T, of course, it's the total sum of squares and cross products matrix. And what we're trying to do is we are trying to see if this H is significantly bigger than this E by taking the ratio of this H and this E. And if this H is big enough, we can reject this MANOVA hypothesis, which states that the vectors of means for the three variables that we're trying to compare together between the groups, this null hypothesis can be rejected. So at least one of these groups of means are different from the rest due to the difference that are stated by the group variable. Now, because that these values, these sum of squares and cross products matrices, because they are matrices, not direct values, we cannot just make a fraction out of them to compare them. It doesn't work like that. So what we do is we can calculate 4 statistics that are for conducting MANOVA, and these statistics are used to properly compare these matrices. So what these statistics do is that we convert these matrices into a numerical, a scalar value, so that we can compare the amount of sum of squares from the group variable and the sum of squares from the error, so that we can see whether or not the sum of squares explained by the different groups are really bigger than the errors. Now, these statistics, after we calculate them, we need to use them to calculate an F value. And in this case, it's not an F value, it's more an approximation of the F value. And we can take these values to the F table so that we can see whether or not the H is significantly bigger than the E. To calculate these values, it can be very easily done in the R Studio environment. But if you are someone who likes to look at the mathematical way of calculating these, we have a website here that shows you how to calculate these statistics using these H and E matrices to calculate these statistics. Now, if you want to see how the F approximations for these 4 statistics are calculated, we have another website right here, and these websites are going to be posted in the description section of the YouTube video, so don't worry about trying to look for these in the presentation. So that was the one-way MANOVA that we just looked at. And in one-way MANOVA, we only have one group variable, so the data of the individuals can only be classified in one way. Now let's say if we have a situation where the individuals in the data set can be classified in more than one way. So in this case, let's say if we have a data set where the individuals can be classified two ways. So we are going to have two group variables. And what's going to happen if these two variables can have a combined effect where the two variables interact with each other? So this is what a factorial MANOVA table looks like, where we have the two group variables here that contributes to the sum of squares of the deviation from the mean of the data set that are due to these two group variables. And of course we have the source of error that contributes to the differences that contributes to the square of the deviation from the mean. And also we have a total right here, which is just the sum of all of these. Now, these two variables, they are going to have their own sum of squares and cross products matrices. The first one is, we're going to call it H, and these are all matrices, these four. The first one we're going to call it H, and this I here, there's no specific reason why it's I just grabbed the idea out of the air. And this E, it represents the sum of squares that are contributed by the error, and these two are sum of squares that are contributed by the group variables, and this is the total sum of squares. Now for factorial MANOVA, the sum of squares, they can be computed in more than one way, and they all have their benefits depending on the situations. So the type 1 sum of squares, it's the best when we have balanced data between the groups. And the type 2 sum of squares, it's the most powerful when there are no significant interaction terms. So let's say that these two group variables, if they do not interact, then it's best to go with the type 2 sum of squares. For the type 3 sum of squares, it's the values calculated are the most accurate when there is a significant interaction term. And for factorial MANOVA, we are not just testing one null hypothesis, we are actually testing 3 null hypotheses. So the null hypotheses are here. So we are testing if group variables A or B, they do not significantly influence the means of the outcome variables between the groups of the group variable A and the group variable B. So these are two separate null hypotheses individually for group variable A and group variable B. Now, the third null hypothesis is that the interaction term of the group variables A and B, that they do not significantly influence the difference between the mean outcome variables between the combinations of these interactions. Now, these null hypotheses, they are going to increase if you have more number of group variables, so be very careful with this. Now, for the factorial MANOVA, it's pretty much the same as the one-way ANOVA when we are trying to look at the significance of these group variables and their influences on the differences of the mean vectors between the categories of the groups. So for this, these are also matrices, so we cannot just do a fraction and compare them, we have to calculate the 4 statistics for MANOVA for them as well. So we calculate these statistics, and then we calculate the F approximations for these 4 statistics and we look up these F values in order to test our null hypotheses. So now we get to the R demonstrations part of the one-way MANOVA and factorial MANOVA. So for the one-way MANOVA example, the data set that we're going to use is called the Bowman education data. And this data set, we only have one group variable, and this variable has 3 categories of different teaching techniques. And these techniques are called basal, DRTA, and strat. Okay? And the outcome variables that we're going to test their means to see if their joint means are different between these 3 categories. They are the grades of the 3 tests that were taken after each of these teaching techniques were done to the students. So in this data set, we have 66 students, and 22 of them are put into the basal category. 22 of them were put into the DRTA category, and 22 of them were placed in the strat category. Now, the basal category is the classical method of teaching, while these 2 are more innovative methods of teaching. And after the students were done with the lesson, they were each given 3 tests. So the null hypothesis that we're trying to test here is that the joint mean, so the mean vectors of the 3 tests, so the grade for the first test, the grade for the second test, and the grade for the third test for all the students, they are going to be different based on the 3 teaching techniques. That's actually the alternative hypothesis for the null. We are going to say that the joint means of the 3 tests are not going to be different based on the 3 teaching techniques. So that's what we're going to do for the one-way MANOVA. So of course, this is going to be similar to the first YouTube video that I made in this 10-part series on multivariate statistical analysis. So the Bowman dataset is contained in an R package called CAR. So first we must install this package. And it's going to take a little while for this package to install. And we're going to use the library functions so that we can access the functions in this CAR package right here. And then we use the data function so that we can access this data set, the Bowman data set. We use its name. And then we attach this data set into the R global environment so that when we click on this, we can get the data set right here. So we have here the group variable, which classifies the individuals, the 66 individuals, into 3 groups right here. And we have here the 3 test grades, the 3 tests that were given to the students after they were subjected to the individual lessons. Okay? So now that that's done, of course, our first step is always to test the assumptions. Now, for this YouTube video, I'm only going to show you how to test for the independent observations assumption, because for the normality assumption and the equivariance covariance matrices assumption, I've already shown you how to do it in the previous video, in the part 1 of this video series. So I'm going to skip that for time purposes. So in order to test the independence of the observations, there is an ICC function that can do this for you. But this function is located in an R package called psych. So we must first install this package and use the library function so that we can access the functions that are inside of this package. And then we use the ICC function in this package to test to see whether or not the correlation between the 3 test grades, the test grades variables, whether or not they have a proper amount of correlation in order to perform MANOVA. Now, I put here Bowman, comma, and afterwards it's 4:6. This means that we're looking at columns 4 to 6. So column 4, 5, and 6. So as you can see here, column 1, 2, 3, 4. So 4, 5, 6. These are the test variables. Okay? These are the test variables. So I'm trying to compare these 3 columns and look at their correlations to see if their correlations are at a medium state. So we run this function here. And what we do is we look at the intraclass correlation coefficients. We look at the first one only, the single raters absolute right here, the type 1 ICC. And the ICC value here is negative 0.4564. Now this shows a medium degree of correlation that's right in the middle to the negative end. So this means that it's not too correlated to the negative side. So this means that we can say that this assumption for the independent observations passes the test. Now, it doesn't matter if this is negative or positive. Even if it was positive, it will still be a medium degree of correlation between the 3 outcome variables that are to the positive correlation end. So it will still be okay. It will still pass the assumption test for the independent observations for performing the MANOVA. Okay? So next, of course, we have the group variable, right? In order to state that this group variable is going to be used as a group variable, we need to take the factor function, which is just a regular built-in function, and we apply this function to the group variable, and we assign this to the name group. This is just a name that represents this. So we run this function. So now this group variable is labeled as a categorical variable. Now for an ANOVA, or in this case a MANOVA, so any kind of analysis of variance, whether it's univariate or multivariate, it takes the form of almost like a linear model. But since this is a MANOVA, we have sort of a linear model that has multiple outcomes. So the multiple outcomes are the test 1, test 2, and test 3. So we need to merge these three into sort of like a single outcome vector. So this function, the cbind, it just binds the three outcome variables together, these three variables. So we run this function, and this does just that. And for one-way MANOVA, we have a built-in function which is just called MANOVA. All letters are in the smaller form. We have this function, and what we do is we put in something that's like the joint outcome of these three variables, this y right here, and we have a little wavy symbol right here, and then we put the group variable here so that this represents the group variable's influence on the values of the joint vector of these three variables, or should I say the joint matrix, because we have multiple values for each of these variables. So we have the y here. So we apply this MANOVA function, all small form, to this. And what we do here is we perform the MANOVA to see this group variable, its effect on the means of these three variables in a joint way. So in order for us to access the information of this MANOVA that was just performed, we need to use the summary function. So the summary function, first we put in the name of the MANOVA that was just performed right here. I assigned this MANOVA to Bowman.MANOVA, and this is just a name. It doesn't do anything specific than giving name to this MANOVA. We put the name first here, and then we put down which test statistic that we want to calculate. Remember the 4 test statistics that are calculated using the sum of squares and cross products matrices. These are the methods to calculate the 4 statistics using R. So we just run all 4 of these functions. So I'm going to make this bigger so that we can see this a little bit easier, see the results. There we go. So this one here, it calculates the Wilks value, the Wilks statistics, I should say. And this value right here is the F approximation for the Wilks value. And this is the p-value of this F approximation. And as you can see, for the Wilks test statistics, the p-value is way below 0.05. Okay, so this is for the Wilks. Now, for the rest of the 3 statistics, we can see that the p-values are also below 0.05. Way below 0.05 right here is, right? So now we can, since it's below 0.05 for all 4 of these test statistics, we can reject this null hypothesis here. So, which means that the joint mean of these 3 tests, the means of these 3 tests, the grades that the students received from these 3 tests are different between these 3 teaching methods. So we reject this null hypothesis here. And if you want to look at how the other, what are the other numbers for the other 3 test statistics, as you can see, this is the p-lie right here, and this is the Hotelling-Lawley. The values are right here, and their F approximations are right beside them, and this is the Roy. Okay, its values are here, and F approximations are right here. So easy enough, right? Great. So now let's move on to the factorial MANOVA example for the R demonstrations. And for the factorial MANOVA, we're going to use a data set. It's called soils. Now, the soils data set is also contained in the same R package called cars. And this data set, it contains the information of soil physical and chemical characteristics. And we have 44 individual observations. We are going to consider 3 outcome variables. We're going to compare the means, the joint means of these 3 variables. And these 3 variables are the pH of the soil, the density of the soil, and the conductivity of the soil. And we are going to consider 2 group variables because this is factorial MANOVA. This is just 2 group variables. It's a simple form of factorial MANOVA. We can even call this 2-way factorial MANOVA. So the 2 variables we're going to consider are contours and also the depth. For contours, we have the categories top, slope, and depression. And the depth, we have these as categories between 10 to 0 centimeters, 10 to 30 centimeters, 30 to 60 centimeters, and 60 to 90 centimeters. Now, I'm not familiar with soil science, so I don't understand what is the significance of these categories, but that doesn't interfere with my ability to test to see if the 3 outcome variables, if their joint means are different between these categories of these 2 variables right here. And the 3 null hypotheses are going to be tested using this factorial MANOVA. So the first 2 null hypotheses is that the joint mean of the 3 outcome variables are not significantly different among the categories of the contours variable and the depth variable. These the means of these 3 variables are not going to be different amongst the categories of the contour and the depth right here. Okay, and the third hypothesis is that the joint mean of the 3 outcome variables are not going to be significantly influenced. They are not going to be significantly different due to the combined effect of these 2 variables. So the interaction term of these 2 variables are not going to significantly influence the means of these 3 outcome variables when they're jointly looked at. Okay? So now that we get to the RStudio environment again, so since we already installed the car package where the soils dataset is located, we can just use the data function to get the soils, to access the dataset in the package. And we can attach this dataset into the global environment so that we can see the dataset physically. So as you can see, we have the 2 group variables here. We have the contour variable, where there are 3 categories, and we have the depth, which also have 3 categories. So and these are the individual observations. Sorry, I said it wrong. There are actually 48 observations instead of 44. Sorry about that. And we are going to be looking at the outcome variables. We have the pH here, we have the density here, and we have the conductivity right here. So there are more variables in this data set, but we're not going to look at them today. We are just going to look at the three that I just pointed out. Okay? So for factorial MANOVA, of course, we need to consider more than one type of sum of squares, right? Now, for the previous MANOVA function, for the one-way MANOVA, this is just a built-in function that was built into the R system. Now, this function right here, it doesn't calculate type 2 or type 3 sum of squares. So in order for us to perform a MANOVA that calculates the type 2 or type 3 sum of squares that are needed for a factorial MANOVA, we need to use another package, and this package is called MAS. So we need to first install this package. We can click yes right here. Okay, so we install, so the MAS package is being installed right here, and we use the library function in order to access the functions in this package. Okay, so now we have two variables that are considered as group variables for this factorial MANOVA. So we must use the factor function in order to state that they are group variables. So we just run this here, and we can run this one here. Now, what I just did here was I just put my cursor here, then Control Enter to run this line right here. So for those of you who can't see my hands right now, that's what I was doing. So it's not magic or anything. So for the factorial MANOVA, it's pretty similar when you're trying to do this in R. So of course we have to bind the three outcome variables using the cbind function right here, and we're trying to see how this how these joint variables are together influenced by these group variables and their interaction terms right here. So this LM right here, it just means we are trying to build a linear model. Okay, so this is just a function, and then we put the quote-unquote model here, right? So this is the outcome. It's the binded form of these three variables, and we have this squiggly right here, this little wavy thing, and we have the individual group variables themselves, and we have the interaction. This is just an asterisk, and this -1 here, it's just, what it does basically is to not show the intercept effect. Oh, and of course this model, it's built using the data set soils, so data equal to soils right here. And this model, it's being named soils.mod. Now in R, this arrow here is the equivalent of an equal sign. So you can have an equal sign there or an arrow there. It doesn't matter. What it does is it stores this linear model into this name, soils.mod. And this is just a name. So we run this line right here. Okay, so now we have this linear model of multiple outcomes with the influence of these variables with the interaction term, and is stored into this name. And to access the information of this model, we go to the summary. We use the summary function to do this. So we run this and just move this up so that we can see the results a little bit easier. And this is the model and its information. So as we can see here, here is the contour variable. Okay, and we can see that for all of these, the p-values are all below 0.05. So the contour variable is significant in influencing the three variables together. So the three variables, their means are different amongst the different categories of the contours right here. As for the depth, the p-values, of course, it's way below 0.05. So we can also say that for the three outcome variables, their means are different amongst the different categories of the depth. But the story is different for the interaction term. These are the interaction terms of the contours and the depth. And as you can see, these are all larger than 0.05. So the interaction term is considered not significant in influencing the values of the three outcome variables. So in this case, we don't have a significant interaction term, which means that we can just use the type 2 sum of squares in order to test our null hypotheses. So now we go to test to calculate the type 2 sum of squares and their four statistical values, test statistics, actually. So I have type 3 here as well, but since we don't have interaction term, we don't have to run any of these 4 lines. You see the type 3 here? Now what we do here is we use the MANOVA function. Now this MANOVA function is different from the one-way MANOVA function right here, because this one starts with a capital M, and this function comes from this mass package. Okay, it's not built inside of the R environment. So we can just run these 4 lines. As you can see, we have the function as the first term. We have, this is a multivariate test, so it's put as true for all of these. And this, we're trying to calculate the type 2 sum of squares. So we have the type 2 here. And we are trying to calculate the 4 test statistics, the Wilks, Pillai, Hotelling-Lawley, and Roy. So we just run these 4 lines. And it doesn't matter if you put the cursor in front of the line or behind the line, it will just run the line that the cursor is on. So just push Control Enter and you should be able to get it. Now why is there a mistake? Don't worry, I can find why this is. we run these 4 lines again? Cannot find function, hey? That's okay. We'll just run these again. Okay, there we go. So sorry about that delay, guys. So as long as you have already run, as long as you have already installed the packages that you need for this analysis properly, like the car package for the soil data set, as long as you run that properly and you run this mass package properly, so that you can access this MANOVA function, you should be able to run these 4 lines. So we're going to run these 4 lines again. 1, 2, 3, 4. Okay. So we have here the type 2 sum of squares, and also the test statistic that's calculated using these sum of squares here. So this is the Wilks, this is the Pillai, this is the Hotelling-Lawley, and this is the Roy. Okay, so for here we can see that for all of them it shows that the interaction terms for the contour and depth, they are all insignificant if you look at all of these test statistics. If you look at their p-values for the interaction terms, they are all way above 0.05. But for the contour and the depth, they are all way below 0.05. So in this case, we can go back to the null hypotheses. So we can reject the null hypotheses for the first 2. So the joint mean of the 3 variables are significantly different among the categories of these 2 variables. And the joint mean of the 3 variables, we cannot reject this null hypothesis, so the joint mean of these 3 variables are not significantly different due to this interaction term. Okay? Alrighty, so now that our demonstrations are done for the one-way MANOVA and factorial MANOVA, now we get to look at the percentage of variance that are explained by the group variables themselves. Okay? So in order to get this percentage, we need to calculate a statistic that's called the partial Eta-Squared values. And this is calculated by 1 minus the Wilks lambda. That's one of the test statistics for MANOVA. And this Wilks lambda is to the exponent of 1 over s. And this s is whatever that's the smaller one for the p, or the degree of freedom of any of the group variables. So the p is the number of the outcome variables. So in the previous factorial example, we had 3 we had 3 outcome variables, right? So this p here would have been 3 for the previous example. And the degree of freedom for the effect, we need to get that from the Wilks test statistic information from the R output. Okay, so any one of these that are smaller. So now to calculate the partial eta-squared values for the one-way MANOVA, what we do is we get this value from the R output. So let's just go back to the R output for a second. And we can go, and this has already been run. We can just go to the summary, function for the Wilks test statistic, and we will be able to get the information that we need for this. So for here, this is the information output, right? This is the Wilks lambda value, so it's right here. This is the degree of freedom for the group variable, so 2 right here, and the number of outcome variables is 3 for this example. So because 2 is smaller than 3, we take the minimum one, so we take 2. Now we calculate the partial eta-squared value using this formula, and the result is 0.205. And this 0.205 means 20.5% of the variance for the grades of the 3 tests taken by the students are due to the difference of the education style. So 20.5% of the variance of the test grades, the variance, the difference between the individual grades themselves and the mean grades. The difference can be explained 20.5% of the difference can be explained by the group variable, which is education technique right here. Okay? So now we go to the Factorial MANOVA for the soils. So for this one, this is a Factorial MANOVA, and we have 2 group variables. So in this case, each group variable will have their own partial eta-squared values. Okay? So to get the information of these, we go to the R output again. So we use the type 2 sum of squares and its test statistics, right? So what we do is we run the MANOVA for the type 2 sum of squares for the test, for the Wilks test. We rerun this so that we can get the information that we need in order to calculate the partial eta-squared values. And in this case, for the contour, this is the Wilks lambda. So we have it here. And we have 3 outcome variables. And the degree of freedom for the contour right here is 3. Why do we have a 2 here? I don't know. So these are all supposed to be 3 right here. Sorry guys, I made a mistake here. So I'm just going to quickly calculate what this value actually is. This is probably not the value. Wow, it actually is the value. What the heck? So guys, this is the partial eta-squared value for the contour variable for this Factorial MANOVA for the soils data set. And of course, this partial eta-squared value, it represents that 78.9% of variance of the pH density and conductivity when joined are due to the difference in the categories of the contour variable. And for the depth, it's calculated the same way. So we use the degree of freedom and the test statistics of the depth right here. So the partial eta-squared value is 0.6837, and this means that 68.37% of variance of the pH density and conductivity of the soil are due to the difference in the depth. Now, some of you might notice that since these two are variables, why is it that this one explains 78% of variance and this one explains 68% of variance? How come these don't add up to the number 1? Now this if you ask this question, congratulations, you are very observant. Now for MANOVA, let's say that if we had a one-way MANOVA, it is the case that if we add this variance explained by the group variable with the error and the total, it should equal to 1. But this only works for one-way MANOVA. For factorial, it's supposed to add the variance of the variables together. Sometimes these values are relatively low, so it might seem like if you add them together, the sum is still much lower than 1. But the variance explained has nothing to do with the sum. So for Factorial MANOVA, expect to have the variance explained by individual variables. If you add them up, they're not going to equal to 1. Okay? So there is another part of this video, but sorry, I haven't made it yet. Now that this video is finished, I'm going to go and make the next video, which is called MANOVA, and this one is also going to include our demonstration. Now MANOVA and MANOVA, I meant to include them together in one video, but while I was working on MANOVA, I noticed that MANOVA is already a big enough topic, and it deserves its own video. So that's why I decided, you know what, I need to split these two up. Otherwise, the video is just going to be too long. So I am off to make this new video now. Hopefully you liked my video on MANOVA. If you find my video series on multivariate statistical analysis helpful, please feel free to give these videos thumbs ups and subscribe to my channel or like me on Facebook. The link is in the description. See you next time, and remember, life is short. Try everything and be everything, and especially don't be afraid of statistics. See you later, guys, and see you at the next video. Bye.